Good morning, good afternoon, and good evening to around the globe, wherever you are. My name is Bjorn, and I welcome you to the webinar for membrane solutions for oil and gas applications, especially for produced water. This will be about the next 30 minutes. It's recorded, and we are a very small group of people today. So again, welcome to the short webinar. Just for the short notice, if you do have any kind of questions, just pull up, just unmute yourself, and then ask the question to whatever you have. For this small group of people, we don't need a big Q&A round at the end. Furthermore, as I said, mute yourself. That would be very polite. If you want to show up on camera, that would be very much appreciated. Other than that, I think I have said more or less everything, and I can introduce my very estimate colleague, which is Jianbeng Wang from PolyCera, and he's a VP of products, and he's with the company and with the membranes from the very early beginning. So he's more or less the absolutely expert. So I hand over this to you, Jianbeng. Take over the people, and as I said, guys, whenever you have any questions, just raise your hand or unmute yourself, and then we can take it from there. Let's go, Jamal.
Okay, yeah, thank you, Bern, for the introduction, and also thank you for all the work behind setting up this. And I'm glad to introduce PolyCera membranes on oil with water, and particularly produced water treatment. And I'm very happy to see some really old friends join this webinar or talk. And some of the content you may already know, but some is our newest development in terms of application. So let me share my presentation. Okay, so again, as Bjorn said, since we have a small group, so we can make this as a discussion as friendly as possible. So if you have a question during the talk, please feel free to stop me and we can discuss your question. But of course, we can also save the question in the end for a very quick Q&A session. So again, just myself, Jinwen Wang. I'm currently the VP product at the PSP US Inc. It's a PolyCera membrane. And today I would like to discuss advanced membrane technology, and especially PolyCera membrane technology for oil and gas produced water treatment. So in today's webinar, the talk, I want to start just a very brief overview of oil and gas produced water. I'm pretty sure some of you are already very familiar with this topic. I just want to provide some related background information, and mainly I want to talk about is produced water treatment. I will, of course, I will go over some conventional gravity-based treatment process, and also the membrane treatment for produced water, and both their advantage and drawbacks with conventional and membrane technologies. And then I will introduce the PolyCera organic metal membranes, the features and benefits, and how PolyCera membrane can be a good candidate for oil and gas produced water treatment. And then I will introduce a few case studies on both onshore and offshore produced water treatment with the PolyCera membranes. And as I said, we can do Q&A during the talk and also after the talk. So for produced water, people call them the hidden fraud because in oil and gas production, every barrel of oil produced, it comes with a 3 to 4 barrel of produced water, water produced along with the oil. And in different area, different region, the number may be different, but in general, the oil company, they dealing with more water than oil. So some of the oil company guys, they joking themselves as they are actually a water company. So it's estimated that globally in 2025, it will be above 40 billion barrel of produced water produced in a year. So that's a lot of water there. in general, unit treatment is also a big market in terms of spending. So a number I can find from 2024 is globally it's about $9 billion spent on treating produced water. So it's about like 30 cents to $10 per barrel, or $2 to $60 per cubic meter, depends on what the unit you are more familiar with. So for general disposal, the treatment cost is gonna be lower, more on the 30 cents or $2 range. But for reuse, especially beneficial reuse, the cost can be high, can be like as much as $10 per barrel or $50 per cubic meter, which is much higher than seawater desalination. And the trend is set to double by 2034. So that's a lot of water need to be treated, and a lot of investment will be made in like a produced water treatment. Also, there is a very strict standard for produced water disposal and discharge. Currently, for the US EPA, the standard for daily max is the oil and grease. It's defined by measured by EPA method 1664. The hexane extraction method has to be less than 29 milligram per liter for daily maximum concentration. For Canada, the offshore requirement, the average 30-day is less than 30 milligram per liter. So in different region, different part of the world, the standards are more or less the same. We talk about less than 30 milligram per liter as a treatment goal. That's for like a discharge. And recently, just this year, the US EPA is proposed to overhaul the produced water effluent like a limit guidelines. So we may see like a more restrict the discharge limit, which means the treatment technology will we will have higher requirement for the produced water management and treatment. So meanwhile, there will be also recently it's get to people's attention is the produced water for the injection well dispose will cause like a earthquake risk in certain regions. It's being recorded and studied in like US, in Texas and the New Mexico region, and there has been proven there's direct link between the produced water dispose activity with earthquake. So that will require more like a treatment and a proper management for produced water, which also means it will add cost. So that's what is in produced water. So in general, conventional produced water is, of course, produced water, majority is water. And also it has hydrocarbons. Those hydrocarbons can be aliphatic, like oil, like a hydrocarbon, and also aromatic, like dissolved, like hydrocarbons, as well as has solids. The solids can be dissolved solids, like salts, and also can be suspended solids. And the origin and the proportion of those three phases components will dictate the nature of produced water, and also will dictate the method of produced water management and treatment. Also, there are like nowadays because different like unconventional oil drilling, so there will be like unconventional produced water, like fracking, flowback water, EOR produced water, like drilling mud, like those different like new kinds of produced water. But in general, they still just hydrocarbons, water, and solids, the three phase, and different concentration, different composition, and which of course require different management and treatment approach. So as previously discussed, there is more water generated than oil by the oil and gas like a drilling process. So how produced water is managed. So when you generate those water, of course, there's mainly two ways to go. One is for disposal, one is for recycle. So disposal is usually including like a surface disposal, like disposal to like a surface pond or surface like a surface water system, which of course need to meet the discharge disposal regulation requirement. And also is a deep well, like injection disposal well, like a disposal produced water underground. So for recycle, it's mainly for recycle use like on-site for drilling process, and also recycle for beneficial reuse out of the oil field. So in terms of current practice, majority of the produced water is actually if disposed into those disposal wells. It's called the saltwater disposal wells, SWD. You may heard about that. So salt water, because it's usually has high salinities for those water. So majority is actually disposed to the wells. And right now, people use more and more, reuse them for hydraulic fracking and try to reuse for the production process. Because the high cost for evaporation and also high environmental risk for surface discharge. So very, very little is being produced water being treated by evaporation or surface discharge. And also nowadays, more and more people is starting to focus on advanced treatment for beneficial reuse, but still the volume is very, very little. But the trend is catching up. For example, a lot of people in oil, like people in West Texas, New Mexico, they're more talking about the reuse of water for two major applications. One is agriculture, irrigation, agriculture reuse. The other one is for data center. The new data center, the cooling tower, the cooling water reuse for the produced water there. So in order to reuse or dispose produced water, they all involve some level of treatment. So conventionally, the produced water treated by gravity-based like process. For example, just a gravity like a tanks, sedimentation like tanks, or by enhanced gravity, for example, hydrocyclone or centrifuge. Those are mechanical enhanced gravity. So for gravity-based removal, like the particle size of the oil matters. So if we have a free oil, which particle size is range about 100 micron or above, the gravity-based method or enhanced gravity is very effective to remove those large like free oil. But if we are dealing with the oil is smaller and smaller, from free oil to dispersed oil to emulsified oil, even dissolved oil, the gravity-based treatment method is become less and less effective. And even for like for example, with centrifuge, you increase gravity by 1,000, even 10,000 times, still you don't see much removal without any other like help. Just gravity only. It's very little removal by those for the really tiny emulsified oil or dissolved oil. So, and also for suspended solid to remove, so we talk about oil, then suspended solid is also a big part in the produced water. So there is so in general, if you have a high oil and a high suspended solid, like tanks, API, CPI separator, centrifuge, it works pretty well in the field. But once you are dealing with a relatively small like oil content and small like solid content, and you're talking about more dispersed oil or emulsified oil, so people starting to utilize flotation. So nowadays, like actually dissolved air flotation depth is kind of the golden standard for the produced water, like oil and wastewater treatment. And the treated water quality is good enough. It's good enough for disposal and good enough for some kind of recycle, reuse on site, but it might not be like good enough for beneficial reuse. And if you have a very low oil content or solid content, and the oil become a more MOSFET and dissolved oil, a media filter, for example, Warner shell filter, is being used and proved to be effective for those applications. So there were in conventional treatment, there are a lot of technologies, process are being used. But one of the biggest issues for those conventional technologies the influent water quality fluctuation, which is quite common in real practice in the like produced water or any other treatment practice fluctuation in the influent. It will affect the effluent, will cause the fluctuation in effluent too. So sometimes you may have the effluent like a water quality not meet the design requirements or not meet the standards, the regulatory standards, cause a system failure. So then next is a membrane separation, which is being widely used for water treatment, process separation, and a lot of separation processes. And in general, there's a 4 type of membranes, like microfiltration, ultrafiltration, nanofiltration, reverse osmosis. And in context of a produced water treatment, microfiltration, ultrafiltration is very effective to remove like free oil, dispersed oil, as well as oil emulsions. And if you have a dissolved oil, then the nanofiltration or reverse osmosis can help to managing the risk of a dissolved oil. So in terms of membrane configurations, commonly used like flat sheet membranes, sphere wound membranes, hollow fiber membranes, tubular membranes, and also model-less like a membrane. So those form factor are widely used like in water treatment and process separation, as well as people try to apply all those form factors in produced water treatment in different like a capacity. So in terms of flow configuration for flat sheet and sphere wound, is mainly like we call like a from like outside in the water from outside pass through the membrane and goes through an internal channel or internal spacer and goes to the effluent or filtrate water side. For hollow fiber, because of produced water has the oil, the content like oil content and super solid, mainly if it's being used, it's mainly also using like outside in like a flow configuration. And for tubular membrane and the model-less membrane is mainly like using like inside out. So it's a flow going to inside and pass through membrane, go to a connector like outside, go to the filtered water as a product. So thermal membrane material in general is like what we normally use inorganic membrane, organic membrane, and also organic inorganic hybrid membranes. So the common material for inorganic membrane and organic membrane are synthetic material. For example, for inorganic membranes like silicon carbide is right now is very like being widely used nowadays compared to the other inorganic membranes. And for organic membranes, there's like a mostly used like for example like a polysulfone, PVDF, PTFE, and also like a PolyCera material. So with membranes, we can use membrane process to replace flotation, hydrocyclone, and media filters to treat like a relatively low oil content and solid contents, and with oil size more in like a dispersed oil, emulsified oil, and dissolved oil, those range. The great benefit for membranes is that it acts as an absolute barrier. So if you have a fluctuant in influent, so in general, you will see constant quality of effluent because it's absolute barrier. So the fluctuation in the influent will not affect the effluent. And so you can safely, it's more safer in terms of meet the treatment goal and discharge standards compared to conventional methods. The biggest problem for using membrane for the produced water treatment is membrane fouling. And the conventional wisdom is the membrane fouling is inevitable unless you get the pretreatment right. So especially in produced water, there's a lot of those called organosilicate deposit and also other minerals deposits will cause those oil and also solids. It form like we call it oil mud, like attached to the surface. It's gonna really affect the membrane performance. Although you can using like a traditional cleaning, backwash or chemical cleaning to recover some reversible fouling and recover some performance, but if you over time, the membrane will see more and more irreversible or irrecoverable fouling due to the incompatible of a membrane material or not a suitable design, and eventually you may have to shut down the system for maintenance or even replace the membrane. So that's just going to the challenge is there the reliable and the economic membrane for produced water treatment? So conventionally, the polymeric membrane, they are not robust enough, and the following will cause decrease the performance and increase the cost. Although the capital cost is maybe less, but the operational cost will be high with traditional polymeric membrane on produced water treatment. So ceramic membrane can prove to be durable and can compare with the oil and also can be recovered by cleaning. But in general, it's still relatively more expensive compared to traditional polymeric, and the capex will be high for utilizing ceramic membrane system. So, of course, ideal solution will be a membrane with a polymeric economics and ceramic performance. That is to treat produced water. So now to introduce what PolyCera we are working on is we are utilizing organic metal material to make membranes, which can provide the polymeric economics and the ceramic performance. So first, also the organic metal materials, they are pure organic polymers. So there's no inorganic or metal organic hybrid. So they are pure organic material. And it just due to its chemical and physical structure, it can have metallic qualities and characteristics. For example, the picture on the right bottom is the picture of the membrane. It's black. So the membrane made from organic metal, it is black and it has organic metal as shining like a metal. So with the nano fiber like organic metal material, we can make a membrane with a strong structure and uniform dense porosity and also high durability. And it is the first time the Nobel Prize chemistry directly adapt for membrane for water treatment. So the main feature is the organic metal membrane is thermally, chemically compatible with produced water, and it has excellent mechanical strength, and there's no, like for example, like no fiber breakage, and also it's not as fragile as ceramic membranes, and also it's intrinsically hydrophilic and oily phobic, so which is suitable for oily like produced water treatment. So in terms of like falling like produced water falling mitigation, the first is it has to be hydrophilic and oily phobic, like oil tolerance. So traditional polymeric material, for example, PVDF and polysulfone, they are intrinsically they are hydrophobic and oilphilic, which means intrinsically they attract oil. So if you have oil in the water, it will more easily to spread or attach to the surface, cause membrane falling and cause performance decline. And also it's harder to clean. So PolyCera organic metal membrane material, as well as a traditional ceramic membrane material, they are intrinsically hydrophilic and oilophobic, which means that they are intrinsically repairs oil. So if you have oil in the water, the oil will not easily attach to the surface, cause falling. Even there is some oil on the surface, it can be cleaned. So for PolyCera membrane, we have tested it can tolerate like 1 to 3% like oil. That will reduce compared to traditional membrane. It will reduce pretreatment and requirement and reduce pretreatment cost. So and even membrane get falling and can be relatively easily cleaned and recovered by just a chemical cleaning, or sometimes even just by hot water. So the other big features for produced water is it has suspended solids. So that will require the membrane membrane can be backwashable. It can backwash, can effectively reduce the suspended solids deposition of the kick layer formed on the membrane surface to recover the performance. So here is a video showing like a backwash. During backwash, the solids and oil attached to the membrane surface is being cleaned during the backwash. So it will lower the falling rate and increase production. and also extend the membrane life and lower the OPEX because backwash. And also the membrane can offer better temperature and pH tolerance compared to traditional membrane materials. For example, it can handle up to 90 degrees Celsius, and which is pretty common you can see on the oil production, especially for the offshore production. And also it can handle pH in like continuously like 1 to 13.5, and also during cleaning, it can withstand pH like 0, even lower pH 0 or higher pH like 14. Also, PolyCera membrane can handle like a pure organic solvents, and for example, like alcohol and aliphatic oil kerosene and aromatic like compounds like xylene. And with exposed to those pure organic solvents, the membrane performance will not change before and after like contact with those organics. Another big factor is since PolyCera membrane is in spare wound form factor. In general, spare wound is known to not handle well solids because the feed channel and the spacer design. But for PolyCera membrane, we are using a corrugated spacer to create an open channel structure for the membrane. So it can handle more solids in the feed without worry about clogging and without pre-treatment. So just to compare like at the oil like wastewater treatment settings, compare PolyCera membrane with a traditional tubular polymeric tubular membrane and also ceramic like a model-less membrane, and just compare the overall cost, like system cost, module cost, replacement cost, and also operational cost like energy cost. So the total cost of ownership, you combine capital investment and the operational cost, PolyCera is 30% lower compared to the next best alternatives. The data is derived from like a real like engineer data project. So in summary, so PolyCera membrane is, because it's a unique the property, it offers the third type of membrane material compared with the polymeric and the ceramic. It offers polymeric economics and the ceramic performance. It has been proven in many of our projects. So in terms of the oil wastewater or produced water treatment, the process with traditional process is centered by DEF, like dissolved air flotation. So for that treatment, it is effective for a lot of applications, but sometimes it do require generate chemicals, for example, to break emulsions, and it will generate a sludge and also generate like volatile organics, VOCs. And also some of the treated water, it have dissolved oil or some nano emulsion, very small, like emulsified oil. You might need additional biological treatment to further remove that. Then you can use for downstream process, for example, ultrafiltration or reverse osmosis for reuse. So with a typical PolyCera process, we can replace and eliminate DEF-based treatment just with, we call that equalization tank, just with oil skimmer on top to skim the free oil, and also with a solid connection at the bottom to collect the settled solids, and then just directly feed into PolyCera membrane system, and treated water can be either for other downstream treatment like our membrane or the ion exchange, or just for discharge, meeting the discharge regulations. So a typical system is we do offer modular design, so you can have a optional like a pre-treatment solid handling. That's the tank I was talking about with the oil skimmer and also the solid connection, and also the PolyCera system is the main part. And also polishing after polishing a step, it can be a oil removal resin or even like a reverse osmosis process to further polish the water to meet the standards. So now I want to talk a few case studies. And the first one is a centralized produced water treatment facility. It was in Bakersfield, California. And the capacity is about 5,000 barrels per day and about 800 meter cube per day. And the water from multiple oil sites is trucked into these facilities and treated for beneficial reuse. So the trucking water, the oil and solids up to 500 ppm, and also it's a relatively high TDS is about the brackish to like a brown. It's like from up to like a 50 like a thousand milligram per liter. So in this facility, the coming in oil will go through a gravity-based oil water separator to mainly to remove some free oil. And then if you go through a softening process, the main reason for doing softening is because there's oil in the back side, so need to do softening so the oil to help the oil process. Then there's some fluctuation to remove for the softening and also the silica chemical removal of silica. Then it will go through PolyCera trains UF to remove the free residual free oil, suspended solids, and the emulsified oil. And then the treated water will go to gradual active carbon to remove any dissolved oil. Then it will go to two-pass oil system, and the final treated water is for agriculture reuse. So the whole plant we can achieve up to 80% recovery, and the cost is 2 times cheaper than deep well injection at the location in this specific location, and all treated water as used by either agriculture or local industry. So we also conduct a comparison study at this site, just compare PolyCera with ceramic, and what we found is compared to ceramic membranes, PolyCera membrane can have higher water recovery, lower energy demand, and also we require less backwash water. So and also the CapEx is much lower, and the overall OpEx it is lower for this process directly compare PolyCera and ceramic. And also one thing we found interesting is we do find that the fluctuation of feed water quality will impact ceramic more than PolyCera membranes. So here the blue dot is feed water oil content, and the orange line is a ceramic filtrate, and green line is a PolyCera filtrate. You can see PolyCera filtrate is much less changing it with giving a feed oil concentration change. So it's more unique and more absolute barrier for the treatment. Another case study is for onshore fracking wastewater treatment for reuse. So this is about almost 8,000 barrels per day, so 1,200 cubic meter per day, and treating water with about 500 milligram per solids, 100 milligram oil. And so the treatment is the final treatment is for mixing fracking chemicals, re-inject into the well for the production. So with a PolyCera membrane, we can achieve over 80% recovery, and treated water it has oil less than 5 milligram per liter, solid less than 1 milligram per liter. And this project was commissioned last year. Another case study is similar, is a hydraulic fracking wastewater, is treating about 300 meter cube per day, almost 2,000 barrels per day, and commissioned in 2021. And this is water treated for re-injection, and with the PolyCera process, the only pre-treatment is just a bag filter, and then PolyCera membrane can treat up to 300 ppm oil and up to 250 milligram per liter solids, down to 5 milligram per liter oil and 1 milligram per solids, and it's good for re-injection. Here's another example. It's a smaller system, but it's a containerized system similar process, just a bag filter and then PolyCera membrane. It also, this containerized mobile system is also being used to treating the fracking fluids for mixing chemicals. The highlight for this project is we finding we can operate this mobile system without chemical cleaning for 30 days. The only maintenance is just a regular backwash. Also, we have a containerized system is treating for the oil. It's a pipeline terminal station. So this is treating oil only wastewater. It's not produced water. It's just oil only wastewater from those they have a buffer tank. When they cleaning the tank, or any cleaning process has some oil only wastewater, and this containerized system can effectively treat those with oil only water with up to 300 ppm oil, and down to the standards is good for discharge. Here's an example for the offshore produced water treatment for this charge into the ocean. So this is a platform treating about 1,000 cubic meter per day, about 6,300 barrel per day. The feed water is has high temperature. It's on average it's about 90 degrees C. At the highest temperature is about 95 degrees C. And the oil and the solids is as high as 500 ppm. So with the PolyCera system, it can treat the water without pretreatment, just a buffer tank, and then to meet treated water less than 5 ppm oil and less than 1 ppm solids, it's safe for discharge the water into ocean. And also can see with the fluctuating in the feed water oil and feed water solids, the treated water oil and solid is fairly stable. And one of the highlights for this process is we are actually managing the concentrate with the traditional method, like traditional settling, traditional air flotation. And here, because it's only the concentrate, which is only like 10 to 15% of the total volume of the draw water. So you can have a much smaller settling, much smaller flotation, air flotation, and to treat those, and then to minimize the waste, and for the continuous operation on the offshore platform. Another offshore project is it started the pilot 2021, and we signed a contract early this year. So the full scale project will be commissioned late this year. So it's a PolyCera membrane will be used to serve like 9 natural gas platforms. So total capacity is 25,000 barrel per day. So it's 4,000 cubic meter per day total capacity. And those are natural gas platforms. So the produced water characteristics are different. It has about 100 ppm solids, 300 ppm oil. And after treatment, the PolyCera can reduce the solids less than 1 milligram per liter, and the oil less than 20. Here is a difference that in the previous case study, we can lower the oil to 5, because in this natural gas platform, a lot of oil is dissolved. It's dissolved hydrocarbons like betash, like benzene, toluene, isobenzene, xylene. Those are dissolved organics. So for those, it will pass the PolyCera UF. So we partner with a resin company with an organic special resin, which can remove those dissolved oil, and also the resin can be regenerated on site by steam. So it can be a continuous process and achieve a total recovery less than, more than 95%. So it's just some summary for the presentation is with organic metal PolyCera membranes, it can offer high hydrophilicity, oil phobicity, and high permeability, and also robustness due to the nature of organic metal material. And it has excellent thermal chemical stability, fault tolerance, which is suitable for produced water treatment. And it offers significant capex and OPEX reduction compared to traditional polymeric membrane, ceramic membrane system. And the element is delivered in cross-flow backwash modules. is suitable and approved in produced water treatment. So again, thank you all for joining today's webinar, and I'm happy to answer any questions like here online, and also, of course, here's my contact information. And if you have any question like offline, feel free to reach out to us. Thank you.
Yeah, thank you very much, Jing Wang. There are actually some questions. Let's start with Emmanuel. You already sent a question into the chat. Just unmute yourself and go ahead.
Yeah, no, it's just to the washing, how the washing may affect the efficiency of the filtration capacity over time, or efficiency.
Okay, so
thank you.
Thank you for the question. So my understanding, the efficiency you are talking about is maybe talking about like a rejection removal efficiency, right?
Right.
And that's correct, because the majority of the membrane fail because of chemical cleaning, because the chemicals attack the material, so it degrade the material and cause separation performance drop. So for PolyCera material, because organic metal, it's very inert. It just do not react to acid and base, do not react to for example, hot water. So I mean, we have run the system. We have run the longest continuous system so far is over 5 years, and we didn't see any drop in terms of separation efficiency. But I will mention one thing is you may see, of course, the membrane, every membrane will see falling, and for difference between PolyCera membrane and other conventional membrane is you see falling and the cleaning. Usually we see it's can much quicker recover the performance. So your downtime is less compared to conventional like a membrane in the oil produced water treatment settings.
Okay, I'll wait for another colleagues that have questions, and I will ask another one. Thank you.
Okay,
perfect. Thanks a lot. Amin, do you want to unmute yourself, or do you want me to read the question? Well, then I will do that for you. What is the max oil concentration, free and dissolved, to the UF membrane in the cases? I think it's a little bit, depends a little bit on the case, but yeah.
Yeah, it's definitely a case specific, and what we have we have tested both on the field and in the our laboratory. So on the field, sometimes we don't see we see as much as we in the case studies I showed today. The maximum usually we see is about 500 milligram per liter. That's everything: free oil, emulsified oil, dissolved oil, everything together, measured. Of course, the oil measured matters. For example, some people using just IR method, some using a exchange, a solvent exchange, and a different method. So I'm talking about the majority just IR standard, IR method measured is about 500 milligram per liter. That's a maximum we saw in the field. But in the laboratory, we have manually make produce oil water. I said up to 3%. We have tested up to 3% oil directly feed into the membrane. Of course, you will see membrane falling with that high oil. But what we prove is that it can be recovered up to 3% oil. The membrane flush performance can be recovered by chemical cleaning.
Perfect. Thanks a lot. Daoud, my friend, do you want to show up and unmute yourself?
I know I can read it. Maybe I missed it, but I'm confused. What is the material of construction for the membrane materials of PolyCera? The second question is, allow me, how you handle the metals in the produced water with the high TDS and metals such as arsenic or barium in the produced water, just in case. Thank you.
Okay, so the material, thank you for the question. So first, the material of a PolyCera is, I mean, what I can disclose here right now, and we are willing to disclose is in the category of, we call that organic metal. So that's a category of the material. And it's a group of polymer material. So it's a pure polymer. It's a polymer, organic polymer-based material, and it can. Why it's called organic metal? Because it can have some metallic properties in under certain conditions. For example, those material can conduct electricity, at certain conditions, and also those material are being used for like a modern battery manufacturing process. And we are using this not just, we are not using the conductivity of those material. We only use them for because the chemical tolerance, they don't react with acid, don't react with base, and do not react with oil. And also there's intrinsic hydrophilic or phobic. We use those material for PolyCera membrane applications. And so metals, okay, so that's a very good question, because there are a lot of metals, like you give example like arsenic, barium, and also there's ions, manganese, like those ions are there. So what we found in practice is since first those metal ions, what we found as they do not chemically react with the PolyCera membrane materials. So that's what we found, and so it will affect performance by like same as other solids, because for example, as ions, you have an increased pH, it will form ion oxide, hydroxide precipitates, and barium, if you have sulfate, you will have barium sulfate precipitates. So those may cause a problem by just same as other suspended solids cause falling. And we found it's very effective to remove those falling by using like a strong acid cleaning agent, because the membrane can handle high strong acid. So we found it's effective to be removed by the acid cleaning.
Perfect. Emmanuel, you had a final question. I give you the word.
Thank you. No, just a curiosity about in very mature water floods. We have water floods operating since 1950. So in some cases, H2S and microbial activity are a big issue. So any limitations regarding the dissolved gases, or should people need to consider a pretreatment to neutralize that water before filtering? So any comment on that, please?
Okay, yeah, thank you for this question. So based on our practice experience, what we have saw in the field, so there definitely the dissolved gases will cause some issue. What we found is the dissolved gas sometimes it cause like oil leakage through the membrane. So we definitely observe that, especially for offshore operations. So what we do is we design a system with we do have a top release. We'll try to release those gas as much as possible. So to our question, yes, those dissolved gas may cause a separation oil leak. Yes, so it will be a problem, and we need to have measures to remove those in the process. Yes.
Perfect. Thank you for the presentation. Thank you.
Thank you very much. If there are no final questions, I can't see anything in the in the chat. Final seconds to raise your question here. Other than that, thank you very much, Jin Beng, for the presentation. Guys, if you do have any further questions, which may come overnight or tomorrow, there's LinkedIn, there's a webpage from PolyCera. There you can find all the contact informations, and you can reach out to Jin Beng or to the team. Having that said, wish you all a great and wonderful day and a great evening, and hope to see you soon. And goodbye to everybody in the world out there. Bye-bye.
Thank you. Bye.
Yeah,
Thank
thank
you.
you.
Bye.